All right, so we start on page 14. We will take our quick look at the calendar. Today we are going to talk about working with radicals. We have a lot of algebra to do today, and I specify that we have a lot of algebra to do today because today is a very algebra intense day. It's no surprise, it's an algebra class, but there are going to be a lot of nitty-gritty detail rules that we're going to look at today, and we're going to kind of move at a brisk pace. So hold on to your hats, but we will look at working with radicals today. Nothing, there's just more topics on the horizon. The next quest is a little ways away, but we'll talk about that as we get closer. But there are a couple of announcements I want to make not related to this class. The first one is one that I made the other day. Currently, student Senate positions are being elected here at GCC. Log into Moodle after class today, read the positions of the people who are running, and vote, okay? Also, you have this referendum regarding the mass purge and whether or not the $9 mandatory fee should stay or if it should disappear from your tuition bill. So you're going to log into Moodle. That's the only place you can vote. If you don't know how to do that, see me right after class. I will tell you. And the Moodle thing will close at noon tomorrow, so you want to vote soon. Okay, on Tuesday of next week, you will have Advising Day, so April 2nd, Tuesday coming up. A lot of students look forward to Advising Day because it's a day where there are no day classes and they have no GCC responsibilities, and that's fine to have that attitude, but that is not the point of the cancellation of all the classes on Tuesday coming up. The point is for you to come in and meet with your academic advisor and think about a good schedule of classes for the fall, maybe also the summer if you're interested. And additionally, there's this whole long list of events that are happening throughout the day. And so there are a lot of workshops. Hopefully you'll find some things that appeal to you. I assume that this document was sent to you. I assume it's going to be posted around. I can email it to you if you just ask me right after class. But there's also a keynote speaker with lunch provided, and I think that means more than just like fruit and crackers. And then one thing that I hadn't seen before that caught my eye was free chair massages from 10 to 2 in the main lobby. So the people organizing this day are doing whatever they can to encourage you to not just call it a day off and stay home. We want you to come out and do some productive things. So come out and take advantage. Yeah. So I am also going to share just a small part of an email that was sent to all the teachers here. The structure at GCC has our president at the top. His name is Bob. The second person, her name is Cher. Cher sent this email to me. Please encourage your students to meet their academic advisor and enroll in courses that will best move them toward their goals and degree or certificate completion. Students may not be aware of new Pell Lifetime funding requirements that make accurate course selection more important than ever for students on financial aid. I think we have talked a little bit about this in this class, but we haven't gone into the nitty-gritty details. Maybe we haven't gone into it at all. Have we talked at all about funding, like Pell Grants in this class? I don't think we have. So recently there have been some changes to the federal financial aid package, and it is now the case that if you are not always making progress towards either the 2-year degree here, or if you have an eye on transferring a 4-year degree somewhere else, there is a good chance you will run out of financial aid before you finish the degree. So you really don't have time to putz around and take, kind of goof off classes. You really need to be focused and always making progress towards the end goal. And this is a change. And so I don't know all the details, but our financial aid office is wonderful, and you can ask them about this kind of thing. But suffice it to say, we want you guys to be making progress towards this degree and maybe another one as well at every moment of your time here. And meeting with your advisor will help you do that. Most advisors right now have like a schedule of their availability for Advising Day outside their door. And certainly you can call or email your advisor to make an appointment. If you don't know who your advisor is, you can contact Julie, but easier is just ask me right after class and I can look it up for you. And again, registration for the summer and the fall begins Tuesday coming up. The earlier you register, the easier it will be to get exactly the schedule that you'd like to build. Just today I got a paper copy of the schedule of classes for the fall and summer, so I'm assuming they are circulating around. They are also live on our website. You can figure out exactly what is being offered when. The books are out. Yeah, so they've already been distributed. So you'll find them floating around. Most up-to-date information is always on our webpage. Any questions, comments about advising and registration stuff? Okay, so like I said, we've got a lot to do today, so we're going to kind of skip around here, just get the highlights. First thing I want to do is jump down here. Again, we're on page 14, and we're going to jump to number 4, and it says, find the square roots of each of the following numbers. So 144 is the first number, and then you guys have seen this symbol right here. How do you read that symbol in English? Square root. And what is the square root of 144? It's 12. If I throw a negative sign in front of that square root symbol, then you are going to throw a negative sign in front of your answer, negative 12. But I want to point out that even though 12 squared is how much? 144. And even though negative 12 squared, that's in the parentheses, is also 144, negative 12 times negative 12, when we write this symbol, it's a little bit confusing because you might wonder, well, is Ian talking about 12 or negative 12? Because both of them will get you to 144. And I want to be really clear. That symbol means the positive number every single time, everywhere in the world. That symbol does not mean the negative 12. It does not mean both 12 and negative 12. It just means the positive one. And I think that that is written up here someplace. Thought it was written. Maybe it's written on the next page. I think it's written someplace. It's on page 13. Oh, is it part of the? Yeah. So okay, maybe that's why I was thinking it was somewhere. It was it part of the group activity here? Yeah. Yeah, there it is right there. Thank you. So when you see square root of 25, we mean the positive number. We don't mean negative 5. We don't mean positive or negative 5. We mean positive 5. That's it. So it's really confusing because there are two numbers that can get you to 25, but the symbol that we have there always means the positive one. Okay, so if we look at this over here, that symbol right there in English is read plus or minus. And so this example is asking for plus or minus square root of 144. Forget about the plus or minus part. How much is that symbol, square root of 144? Is 12. So I'm going to write the 12. And then I'm going to copy in purple the plus or minus that was sitting there in the front. So it's sitting there. So at this point, really the only way that I'm going to expect two answers from you, which is what that plus or minus 12 is if I give you a plus or minus to start with. If you just see a square root symbol, it does not mean both the plus and the minus. It just means the plus every single time. Okay, moving on, we're going to take a look at number 5, which has some examples of radicals that are not square roots. So the 3 in the front of this radical symbol means cube root of 64. So let's take a step back to the square root of 64. How much is it? 8, because 8 times 8 gives you 64. The cube root of 64 is a different number. Something times itself again is supposed to give us 64. What is it? It's 4, since 4 times 4 times 4, 3 of them is 64. Okay, so the cube root of 64 is 4. And then in this next example, it talks about the fourth root of 16, which means I'm looking for some number times itself how many times? 4 times. It's supposed to equal 16. What number is it's 2? And in some sense, like, unless you've got these numbers memorized, every one of these problems is like a small miracle, because if I say find the fourth root of 16, you just have to pull out of a hat the magical number times itself, times itself, times itself 4 times is going to give you 16. Now, I think that probably you have memorized a lot of the square roots, like square root of 144. You probably didn't refigure that out when you saw it. You probably just said, oh, it's 12. It was just this miraculous thing that happened. But sometimes it's harder to have these miracles. And so if, for example, I gave you like the cube root of 216, I'm guessing that not many of us just have that number. 216 is a special number. But you do have a special table on the very first page of this packet. So let's just take a quick look at that table. So the very first page, it says it's going to be helpful on homework, and you're also going to bring it with you to the quest that's coming up, and the test that's coming up, and the final exam. So you'll have this with you, right? Michelle? Yeah, the question is, do we just have to know? So let's answer the 216 question here, and then we'll answer Michelle's question. So the cube root of 216, you're looking for 216, but where will you look for it? Under the perfect cubes column, because this is a cube root problem. So you find 216, oh, there it is. What's the answer to this problem? It is 6. And this is the miracle that I was talking about, right? Like, it's just a miracle. And Michelle is asking, can we figure it out? Well, not using the table. It's just a miracle, right? Either you know the number or you don't, and hopefully you can find it in the table if you don't. If you don't have the table in front of you, there are certainly ways to use technology to help you find the answer. So on this particular calculator, there is a cube root option. It's there at number 4. And so if I just ask it for the cube root of 216, it knows that it's 6. But even if you don't have a fancy calculator that knows that, you could just start guessing. What if I just ask myself, maybe the answer is 5? Is the answer 5? No. I want to get 216. I got 125. Is that too big or too small? That's too small. Okay, so it wasn't 5. Let's try 7. 7 cubed. Is it 216? No, but it's too big. Okay, let's try 6.3. And you can play this game for as long as you have patience for. And even if the number isn't nice, like 6 is nice, you can get as accurate as you want as long as you have enough patience to get there. So there are ways to figure it out, but it's kind of this like intelligent trial and error that will eventually whittle you down. There, I don't have any equation that I can give you that you can solve this equation and it will just zip out the answer. There are approximation methods using like higher mathematics. We're not going to get into them, that will get you the answer a lot faster than this trial and error thing. Good question. Any questions on how to use this chart? This is going to be very helpful to you when you do the homework tonight. Okay, so let's go back. I think what's that, Katrina? Oh, okay. So I think we might be done with page 14. So let's go on to page 15. Okay, and we'll look at number 6. Can we start with Ben? Yeah, so here's some vocabulary that I did not talk about on the previous page, but the radicand is the thing inside the radical. Radicand is the thing inside, and the index is the number that's the tiny number in the front. And so why was it the case that the cube root of 64 was 4? Or well, we can write that in a slightly different way. Would you guys agree that 4 cubed is 64? 4 times 4 times another 4. So then instead of the 64 that's in purple there, I could put 4 cubed because it's the same. That's what I've done. I'll put it in purple in here. And so we believe the cube root of 64 is 4. Written another way, the cube root of 4 cubed is 4. And when it's written that way, we're going to start to kind of develop this nice little shortcut. If you have a cube root of something that is cubed, essentially those two things cancel and we just get the 4 that's left over. So like in a very real sense, that cube root symbol and this cube goes away and we just get plain old 4. And in the very next line, 4th root of 16 was 2. But instead of 16, that's the same as 2 to the 4th. And then again, in that same real way, the 4th power inside cancels with the whole radical symbol, including that little 4 in the front. Okay, so we'll go to subtap for this we refer. to the fourth. 2 to the fourth. So let's take a look at this next example. Here I'm going to ask you to simplify the cube root of x cubed. It's different because it doesn't have the numbers. It's not going to be on your chart anywhere. But if we buy into this canceling idea, then the cube root and the cubed are perfectly opposite each other. So what do we have as the answer? It's just plain old x. That's it. If you see a cube root and right next to it is a cube, they cancel. And then on the next one, the fourth root of x to the fourth, also x. So if by coincidence you're given a radical where the little number in the front matches the power inside, you just cancel them and you get x. Unfortunately, I'm not going to give you ones that are that easy. So let's come down and look at how to handle them when they're a little bit tougher. So the cube root of x to the sixth. I would have been a lot happier if this 3 in the front had been what number? I would have been really happy if that was a 6. But I can't change it. It is what it is. But I do have a little bit of control of what's inside. What would I be really happy to see as a power right out here on above the parentheses? I'd be really happy if that was a cubed, yes? Because then whatever is in the parentheses, that's going to be the answer. If you have cube root of something cubed, you just get the something. So the question is, can you somehow put something in the parentheses that's really x to the sixth after I cube it? X to the 2 is the right answer. So what we just did there is like a backdoor approach to creating x to the sixth, but it wasn't helpful to me as x to the sixth. It's helpful to me written as something cubed. And you guys know the property, right? What do you do to the powers when you see things like this? You multiply them. So we just turned in the sixth power into something that's cubed. And then we like to cancel, so we will cancel. And what do we get as the answer? X squared is the right answer. So then what I'd like to do, I'll write the kind of basic form for this next one, and I'll ask you to do it and the one below. But I'd really like to see this guy raised to what power? I'd really like a third there. So see if you can fill in the number in the parentheses so that you actually still have the same x to the 12th you had before, and then write your answer, and do the same thing in part C. So check with your neighbors on this one. Okay, for part B, what goes in the parentheses? X to the 4. Everybody buy that we're just rewriting x to the 12th, but in a much better way, because then what's the answer to this whole thing? Is x to the 4th. And then the same idea on the last one. Cube root, what goes in there? X7. And so then the final answer here is x to the 7th. And so there's actually a really easy shortcut, but before we say the shortcut, I want us to understand this thing that we built. Do we buy, like why did we write these numbers, these things here in black? Like do we understand where they came from? Any questions? Okay, so then what's the shortcut? Well, your job is to try to come up with a relationship between x to the, so the cube root of x to the 6th somehow gave me a squared. Cube root of x to the 12th gave me a 4. Cube root of x to the 21 gave me a 7. What can we do with the 21 and 3? We can divide. 21 divided by 3 is 7. 12 divided by 3 is 4. 6 divided by 3 is 2. That's the shortcut. And it works. Go to the very next page. You will see right up here that shortcut written out. Now it's an n and a k instead of being two specific numbers, but we're supposed to divide. Which one goes on top? The one in the front or the one inside? Which number went on top? Did we do 3 divided by 21 or 21 divided by 3? 21 divided by 3. So the number in there divided by the number out front. That's exactly what this says. The number in here is k divided by the number out there. K divided by n is written there. See it? So if you have that shortcut, it makes doing the previous problems really easy, really quick. So for this first example, x to the, you take 24, you divide by 3, 8. That's it. X to the 8th is done. But this is only easy if you have that shortcut in front of you, and if you don't know the shortcut, or if you're not sure, was it 24 divided by 3, or was it 3 divided by 24? Just, you have to kind of go back to the first principles like we did on the previous page. You can figure this out if you don't remember what you're supposed to put up there. But let's go ahead and use that formula a whole slew of times real quick, and just go ahead and fill in all of those, A through F. That's it. Yeah, F looks a little bit different. Good question. Yeah, so, okay, so I've got the first 5 up there. Do we agree with those 5? So, yeah, what do you do when there's no number in the front? I mean, there is an implied number there, but we just choose not to write it. And I've heard some people say 1, and I've heard some people say 2, and we'll get different answers, right? So how about we just think about this back from first principles. X to the 24. I really want x to the 24 to equal something times itself because it's a square root, right? The square root of 25 is how much? 5, because 5 times 5. 5 times itself, 2 of them. So I need something times itself, 2 of them, to be x to the 24. What power should I put? Is it x squared? What do you get when you multiply these x's together? X to the 4th. You add those powers, right? So I don't want x to the 4th. I want x to the 24th. What do you get when you add those powers? 24. This is right. X to the 12th times x to the 12th is x to the 24. So this is the right answer. So how is it consistent with what we had before? Well, the number that we choose not to write is a 2. It's a square root. And because we deal with square roots so often, we just decide we're going to be universally lazy and we're not going to write it if it's a 2. If it's any other number, you got to write it. But if it's a blank space, we and the rest of the world assume it's a 2. And once it's a 2, then our division property will give us this same answer, right? 24 divided by 2 is 12. Questions on that? So I'll say this, if you saw these 6 questions on the upcoming quest, you'd be pretty happy, right? These are all straightforward, only because we have this rule right in front of us. The problem is that these things are going to be mixed in with all the other problems that relate to all the different kinds of power exponent rules. And there's so many exponent rules that it's really easy to kind of merge them together. These problems were all straightforward because they're all the same technique and we just did one and then you can do the rest. But there are a lot of things you can think to do with 3 and 24, and only one of them will give you the right answer, which is 8. You could try adding them, you could subtract them, you could divide them, you could multiply them. I could be really mean. How much is, let's do this, square root, let's do actually 4th root of x to the 64. What do we do with those powers? Divide. So 64 divided by 4 is 16. Fair enough. How about the cube root of 64? If you're not sure, you can look on your chart. That's just a number. So hopefully that number is on the chart. It is. It's 4. How about the cube root of x to the 64? It's messy. It's messy. Katrina said it's not an easy number. Yeah, it's a decimal. It's a fraction, right? So I say it can be tricky because on the one hand, cube root of 64 is perfectly nice, but the cube root of x to the 64, it might be tempting to say, oh, I'm supposed to take the cube root of 64, which is a nice number, but you're not supposed to do that at all. So you got to be really careful. And, you know, like I will give you opportunities. You know, I'll give you something like, I don't know, square root of x to the 36. There's one answer to this problem. It's x to the 18, but it's very tempting to do what? to take the square root of 36 and say, oh, it's x to the 6th, right? It's not. So you got to really know your rules. There's a big difference between just the square root of 36, which is 6, and throwing an x in there, which puts the 36 on the power, which leads to a completely different answer, right? So we got to really know our properties. Okay, so speaking of a lot of properties of radicals, we're about to learn two more. So in number 11, it says find the value of each of these. First one, square root of 9 times 4. So first thing to do is just 9 times 4. How much is it? It's 36. And how much is the square root of 36? 6. A completely unrelated question is part B, which says first take the square root of 9, then take the square root of 4, multiply them last. How much is the square root of 9? 3 times the square root of 4, 2, which is 6. And this is not a coincidence that we got the same thing. So here is a property that we are now going to use a bunch. This is first one down here in number 12. We'll call it the product rule for radicals. Product because we're multiplying. If you have the square root of a times b, you can separate them into two different square roots and multiply at the end, like we just did. But even more than being true for square roots, it's actually true for every single root, cube root, fourth root, anything, which is why there's a little n in the front to indicate this is a general rule for any radical that we have. Let's do part C. The square root of 9/4. Don't think about separating it because that's what we're going to do in part D. But let's just think, can we find a number that when you multiply by itself, you get some number that when you multiply by itself, so we got one copy and another copy of the number, you get 9/4. So what number is it that we can multiply by itself to get 9/4? It's 3/2, right? Because what do you do when you multiply fractions? You go straight across. So, right, 3/2 is the answer. But that looks kind of nice actually because the square root of 9 is exactly 3 and the square root of 4 is exactly 2. So again, not a coincidence. Radicals work really well with multiplication, as we've seen, and then also with division. And this is the second property here. If you have the square root of a fraction, you are perfectly welcome to split it up into two different square roots and then do the fraction, do the division last. And that's true not just for square roots, but for any roots. So let's take a look here in number 13. So simplify the following radical expressions, and each one can be simplified so that no radical remains. And then there's this funny direction. You can ignore that detail for right now. Assume all the values are non-negative. We'll see why that's important in just a few minutes. But can you guys see if you can work with your neighbors and get answers to A through F? So let's do these last three together. I appreciate all the energy that's going into these problems. One of our properties of radicals says that if you have two radicals multiplied together, you can make them one big radical and multiply them together inside. So I think that's a good thing to do in this case because, for example, the fourth root of 2 is not a nice number. So I really can't do anything with that. And the fourth root of x squared, I really can't do anything with that either. So let's merge them together, and then it's going to turn out we will be able to do stuff with it. So when we multiply all these things together, 2 times 8 is 16, x squared times x squared, add those powers, we get x to the 4th. And now I'm going to write another step that I don't need you to write out, but I'm just going to be very detailed here. This is 16 times x to the 4th, right? And when I have multiplication in a radical, I can split it up into two radicals. So I'm going to write the fourth root of 16 times the fourth root of x to the 4. Yes? And it seems like, well, I haven't really done very much because I had two radicals multiplied and now I have two other radicals multiplied. But the good thing is that these two radicals are both nice. How much is the fourth root of 16? It's 2. How much is the fourth root of x to the 4th? It's x. The answer here is 2 times x. So what's 2x? 2x. That's what I'm saying. It's 2x. Did I say it was 16x? Oh. On the record, I apologize. It is not 16x. It is 2x. That sounds good to me. Yes. I'm not. You shouldn't trust me anymore. So, all right, let's take a look at part E. Part E, I see a fraction. I'm going to try to merge them together and make one radical first. 8y 10 over y 4. Right? That's our property. Merge them together. And now we're going to clean this up. This is a cube root, so 8 has nothing to go with, but y to the 10 over y to the 4. What do we do with those powers? We subtract them, and we get y to the 6. And I don't have a fraction anymore. There's nothing down there, so that's it. And again, you don't need to write this step, but I'm going to highlight that I'm really thinking of splitting this thing up into two different guys because multiplication works very nicely. You can split things apart. And then the cube root of 8 is a nice number. It's 2. What do I do with these powers here? We take these powers and we divide. So I squared is the answer. There we go. 2i squared. Okay. In part F, we're going to distribute because multiplication distributes over subtraction in this case. So I have I have square root of 3 times square root of 12 minus square root of 3 times square root of 48. Yes? So we distribute. That's the only thing we can do. None of those radicals are nice. So what we'll have to do here is merge together the first two radicals separately from the last two. Yeah, right? Because we can make two radicals into one when it's multiplication. Minus 3 times 48. So 3 times 12 is 36. Oh, finally, a nice number to have under a square root. And then 3 times 48, is that 144? Great, another nice number under a square root. Normally, I'll pause for a second, let people catch up with the writing. Normally, this would be the end of the ball game. If it was square root of 35, we couldn't do anything. And under no circumstances could I do something with the 36 and the 144, like maybe subtract them together. Square roots just don't work nicely over subtraction, like it is here. They work great for multiplication and division, but they don't do anything for subtraction. So normally that would be the end of the ball game and we're done. In this case, it happens that they both turn into nice numbers. And so -6 is the final answer. Okay, so moving on to the next page. It says these radicals can also be simplified, but the final answer is still going to have a radical in it. So here's the basic idea. Square root of 18, is it nice? It's not. But you can't say that. Yeah. But if we could maybe split 18 up into two numbers multiplied together, then I could perhaps split those guys up because multiplication is a nice thing. So give me a number that goes into 18. 3 goes in, right? Don't write this. 3 times 6, don't write that. It's true, yes? And then I can split it up and I get square root of 3 times square root of 6. Don't write that. It's true, yes? Is the square root of 3 nice? Is the square root of 6 nice? No. So I've done true things, but I'm stuck. I can't go anywhere at this point. Maybe a different way to factor 18. 2 times 9. And I'm hoping one of those numbers strikes you as like, oh, that's going to be nice when we get there. Which one is nice? Is the 9. So I'm going to put the 9 first because that's going to be a nice number inside the radical. And then the 2, it will just be left there at the end. It's fine, but the 9 is nice. And so then we split it up. Square root of 9 times square root of 2. And we get 3 times the square root of 2. And that's it. And we call that thing simplified. 3 times the square root of 2. So let me just convince you that the calculator agrees that these are the same. Oops, square root of 18 is that. 3 times the square root of 2 is exactly the same thing, okay? So they are the same. All right, so then the basic idea here is that you're going to factor into some nice stuff. The nice stuff in this case was the 9, and the leftovers, which was the 2, okay? So we've got the nice thing, and then whatever's left over. And usually the leftovers are not very good. What can I say? So we're going to do the same thing with part B. X to the 13. What's the invisible number right here that we don't have to write? I'm going to put it anyway. It's a 2, right? Now, x to the 13th is not a great number in there because what am I supposed to do with the 13 and the 2 is divide them. And that doesn't go in evenly. So what I'm going to do is I'm going to take that x to the 13, I'm going to split it up into some nice x's and then some leftovers. What number less than 13 would be really great to have in there? How come 13 is no good with the 2? 13 is prime. And in particular, 2 doesn't go into 13, right? When I try to do the division, 13 divided by 2 doesn't go in evenly. So I'd really like a number that does go in evenly. So 2 doesn't go into 13, but 2 goes into 12 and 10 and 8, right? So don't write this just yet, but for example, I could take that 13, I could split 8 of them off, and how many would be left over? 5, that's still 13. And then I could very nicely handle the square root of 8. You're still not writing this, because the square root of 8 now works very nicely with the 2. But the x to the 5th has some nice stuff in it as well. So better than going 8, we want the biggest thing that we can put in there. So give me the biggest number you can find that's nice, but still less than the 13, and that's the 12. So we're going to split this up into x to the 12th, and then how many x's left over? 1. You don't need to write that, but I'll put it there just to really highlight. We still have 13. And now we'll use this nice property of radicals. I'll write in my invisible 2 on this one. What do we do with the 2 and the 12? We divide, so that really gives us x to the 6th times square root of x. That's our answer. Yeah, so simplified is in the eye of the beholder, but I'm just sharing with you what my eye and what other math folks' eyes likes. Yeah. Let's take a look at part C. Take a look at part C. Cube root 32y to the 17. Okay, I'm just going to start writing 2 radicals here. We're going to skip 1 step in the middle. The first radical is going to contain all the good stuff, and the second radical will have the leftovers. We've got the nice stuff in the front, leftovers at the end. 32, is 32 a perfect cube? It's not. But maybe we can factor 32. So go back to page 1 on the packet. You're looking for a perfect cube, but it has to go into 32. So 27 is a perfect cube. Does 27 go into 32? Does it go in evenly into 32? Doesn't. So we want another cube. I want something that goes perfectly into 32. 8, right? 8 goes into 32, and 8 is a perfect cube. So 8 is part of my good stuff. So I've got 8 in the good one, but I still need 32. 8 times how much is still 32? Is 4. So I'm going to circle in black that 32, which is 8 times 4. 8 is good, 4 leftovers. The y to the 17 is a bit trickier. Does 17 go nicely with 3? No, because we know we're supposed to divide them. So here's what we want. We want a number that 3 goes into. It's got to be under 17. 15 is the best answer. You have 17 x's to play with, or y's to play with. You're grouping them so that you have a number that's divisible by 3, but you only have 17 to play with. So you can't build it up to like y to the 18th. Right? If it was y to the 18th, that would be great, but I don't have 18 y's to play with. I have only 17. So the best we can possibly do is branch 15 of them off there, because 15 is perfectly divisible by 3. And then how many y's are left over in the other one? Is 2 y's. So we have y squared over there. And then let's put our answer. What is the cube root of 8? 2. The cube root of y to the 15 is y to the 5. We divide those powers, and we got a nice number. We got a 5, because we chose to put 15 of those y's in the first part. And then the cube root of 4y squared, we can do nothing with. That's our answer. All right, so we could say rewritten. Rewritten instead of saying simplified. We're simplifying the radicals. I'm playing with radicals. Okay, so we've got the good stuff in the front, leftovers in the back. Moving right along. Are we still holding on to our hats? Doing okay? I warned you at the start, right? There's a lot of algebra today. Let's go to this square root of 9 plus 4 compared to the square root of 9 plus 4. Square root of 9 plus 4 plus square root of 4 says do the square roots and then add. Square root of 9 is 3 plus 2 is 5. If we do the add first and then the square root last, what do we get? Square root of 13. Yes? Is this the same as this? No. So this is supposed to illustrate that you cannot simplify, you can't split up square roots when there's an addition or subtraction. So we've already seen this works perfectly well. You're allowed to do the square roots first and multiply last. We saw that. Division works really well. But under no circumstances are you allowed to split up the square root of sum or subtraction, as Sam points out. So let's get 16 read aloud. I think we're up to Tenzin. Are you up for reading today? Okay, let's go to Teresa for 16. Thank you. So it does not work. Square root of x plus y can't be simplified. We don't do anything with it. Neither can the square root of x minus y. And this isn't one of these things where, like, I know some more math than you guys and I'm holding back on you. There's nothing to do. So we gotta avoid the temptation to do stuff like, okay, square root of a squared plus b squared, split that up into this, right? Looks reasonable. And the square root of a squared is just a and then plus b. It looks good. So it's very tempting on a test if you see square root of x squared plus 4 to say, oh, square root of x squared is x plus 2. Wrong. There's no way to fix it. There's just nothing to do with sum inside of a square root. Same thing with minus. Okay, in number 17, talks about adding and subtracting radicals if they are like radicals. So you have seen the word like before because you've used it for like terms. So if I gave you like 3x plus 2x squared plus 7x, which ones of those are like terms? The 3x and the 7x. So what you can do is you can mush them together and get how much? 10x, right? You can't do anything with the 2x squared, but you can mush the 3x and the 7x. In the same way, you can mush together radicals if they look exactly the same, like x and x. So in part A down here, it says 5 radical 7 plus 3 radical 7. This guy and this guy are both exactly the same. They both look like x. If it were 5x plus 3x, what would the answer be? 5x plus 3x, the answer is 8x. 5 radical 7 plus 3 radical 7, the answer is a radical 7. It works just like the x. But there are tempting things to do that are wrong. It is tempting to maybe add the 7s together and come up with square root of 14. Or maybe multiply the 7s together and get 49. You don't do anything with it, just like you just copy the x. For the next one, 8 radical 10 minus 12 radical 10. So I like the radical 10 and negative 4, right? 8 minus 12. Let's take a look at this next example. Square root of 12, square root of 75, square root of 27. Are any of those like radicals? No. So we can't do anything in the current form. But we have seen ways to rewrite radicals. For example, back up here, square root of 18 was actually exactly the same as 3 radical 2, right? So maybe if we rewrite some of these radicals, they'll change. 18 became a 2. Maybe we'll have lots of things that become 2's. So that's what we're going to do. So down here, I start with the square root of 12. You want good stuff and you want leftovers. You want to factor the number 12 so that one of the factors is a perfect square. 4. And what's left over? 3, right? That's our 12. 4 times 3. Could we have done 12 is 6 times 2? We can do it, but it's not helpful because square root of 6 is useless and square root of 2 is useless. And I'm going to copy the rest of the original, minus 2, and now I'm going to play the same game with the 75. And this is kind of another miracle here. You're looking for a factor of 75 that's in the list of perfect squares. So again, you're going to have that list in front of you. So we're looking for a number in the perfect squares list that goes into 75. Anybody find one? Does 64 go into 75? Does it go in evenly? 5 goes into 75, but 5 isn't in the list. 25. Evenly. So, yeah. Right. So 3 doesn't go into 17 evenly because there's some stuff left over. But 3 goes into 15 exactly 5 times, nothing more. So this is 5. This one is 5, and then some extra stuff. So to say it goes in evenly means when you divide, you just get a straight number with no remainder at the end.
I don't get where you came up with
The 3 in the bottom? I just made these examples up. So I would say that 3 goes into 15 evenly. 3 does not go into 17 evenly. The 3 I just made up. For this example, here's what we're looking for, Michelle. It's the 75. I need some number that goes into 75. The only choices that are worth anything to us are the ones in our perfect squares list. So I'm just looking at this list right here, and I'm looking for a number that goes perfectly into 75. If I look at the first number in my list, this 4, I'd say, okay, does 4 go into 75 perfectly? The answer is no. So 4 is not good. What's the next number in my list? 9. So and you were, yeah, you're picking the biggest number that's still smaller. Right, that's still smaller than the 75. Yeah, yeah, it's more than that. We need it to go in perfectly. Yeah. So where's our number in this list that goes into 75? Is the 25. So that's the number that we'll pick. Let's come down. Okay, so 75 is what we were working with. 75 is 25 times some leftover, 3. Plus, I'm copying the thing in the front, 7. I'm going to split up and get 2 radicals. Yeah, 27. You got to factor 27. The useful way to factor it is 9 times 3. Yeah, it's a good question. All of this is multiplication. And we usually don't write it, but there's a hidden multiplication in between the 7 and the radical. Okay, let's keep on trucking here. This equals, square root of 4 is nice. It is. 2. And then the square root of 3 is leftover. It's just going to be there for the rest of the problem. Minus 2 times square root of 25, 5. Square root of 3 is just there. Plus 7 times square root of 9, 3 times square root of 3, which is copied. All multiplication. Okay, 2 radical 3 I like, but let's clean this next one up. What can we do with the 2 and the 5? Let's combine by multiplying, so -10 root 3 plus 21 root 3. And then finally, after all that, we have some good news, because this, and this, and this are all like x. They're all the same radical. So we can merge them all together and get a single term. So we're doing the 2 minus the 10 plus the 21. What is it? Sam says 13 radical 3. Teresa agrees. So this right here came from 2 minus 10 plus 21. Yeah, this one is simplified, right? And so maybe here's part of the reason why we care about stuff like square root of 18, rewriting it as something that might be useful to combine with other terms. Okay. There's a lot of steps in that problem. It gets easier with practice, I'll say that. Ben, you said not even close? This is a radical 3 right here, not a 2 times 3. It was this guy.
Yeah, but what I did is I took those 2 and
Oh, when they're multiplied, they become 3, but you can't do anything with them when they're added except combine the like terms like we did here. So you can't mush the radical 3's together. Okay, moving on to the next page. Okay, let's take a look at the square root of 5 squared. How much is 5 squared? 25. How much is the square root of 25? 5. And maybe it feels like that was actually kind of a silly example, because what's the invisible number in front of this radical? Is a 2. And if you have a square root and a squared, they're opposite. They just cancel each other. So of course, we start with 5, we end with 5. Let's take a look at part B. What do we get? How much is -5 squared? It's positive 25, right? And not knowing where this thing came from, how much is the square root of 25? It's 5. Did the square root and the squared just cancel? It didn't. What would we have gotten if we had just, we would have gotten -5, right? We're saying like square root and square, they just cancel, you just get 5. Square root and square, they cancel, we should get -5, but we didn't. Because that squared on the inside got rid of the negative sign, and now once the negative sign is gone, you just get the +5. So that squared on the inside really kind of messed up our intuition, which is that square root and squared cancel, they're opposites. So here's the idea. Yes, they cancel, except you are always going to get a positive number. Even if you started with a -5, it'll become +5. Does anybody know the math way that we have to describe that kind of thing, where you take a number and no matter what, you make it positive? Absolute value. You guys heard that phrase before? Absolute value says you take a number, make it positive no matter what. So then how much is, and then here's our symbols for absolute value. How much is the absolute value of 5? It's 5. If it's already positive, you do nothing to it. But the absolute value of -5 is also +5. So it just says take a number, make it positive. Good. And how many spaces is always a positive number? Yeah, perfect. Right, for both of those numbers, it's +5. Good. Okay, so then what we can say here, it looks like the square root of a squared should just be what? It should just be a. That's what it feels like. Square root, squared, they undo each other, but in reality, it's a little more complicated. It's absolute value of a. You picked up on that. Okay, so the next question is, does that pattern hold for other roots? This is a square root thing, but if, for example, we saw the cube root of a cubed, it seems like the two choices are either absolute value of a, or maybe it's just a. You know, does it just work nicely in that case, or is it just always absolute value? Maybe this doesn't even seem like a natural choice. Maybe it just feels like it's always absolute value because that's what happened. So let's take a look at a quick example here, this first row. The cube root of 5 cubed. What does it feel like the answer should be without doing the work? It feels like it should just be 5. Let's do the work now. How much is 5 cubed? You can use your table if you want. It's 125. And then the cube root of 125, again from the table, is 5. Okay, so we were right. We just got 5. We expected to get 5. How about for the next one? What number are we going to get if the same absolute value pattern from up above still holds? We're going to get +5 again, right? That negative is going to disappear because it disappeared before. But when you actually take the -5 and cube it, what do you get? You get -125. Did that negative vanish like it did when we squared? No, it's still there. And the cube root of -25, anybody know it? You want some number times itself again. Yeah, it's -5 because -5 times -5 gives you the +25. But then times another -5 brings us back to negative. So the answer here is -5. That's right. If it's an even, yeah, that's it. That's the intuition we're building here, is that the evens lose the negative. If you square that negative number, you lose the negative. And so you're just going to get a positive no matter what you started with. But when you cube that negative number, it stays negative. You still have that negative around, and it will still be in the answer. So here are some facts. Symbols look complicated, but hoping that we've built up to it. Both of these things ask us to write down the nth root of a to the n. Forget about the absolute value business. What does it feel like the answer should just be? Should be a, right? The nth root and the n cancel. So I'm just gonna put a for both of them. So it's not plus or minus, but one of them will be absolute value. So in which case did that -5 stay in the answer? Did -5 stay when we had a squared or when we had a cubed? When we had cubed. So if the thing is odd, this is Sam's observation, if the thing is odd, you just keep it. So that's what it says. If n is odd, you just get the number itself. If it happened to be negative, so be it. But if n is even, then the number that comes out is always what kind of a number? It's always positive. And so that one has absolute value. So I wrote some little silly mnemonics. I don't know if they'll be memorable to you, but the idea here is that one of them, you just leave the number as it is, and in the other one, you make it absolute value. You make it positive. So here's what it says. If n is odd, then don't, and is ODD underlined in yours or no? Yeah. Okay, so I have misspelled the word modify to try to get the word odd in there. So if n is odd, then don't modify it. Right? Odd, don't modify. But if n is even, and maybe even is also underlined in the word revenge, if n is even, then the absolute value gets its revenge. Okay? So even, absolute value, revenge. So I know that we're already 15 seconds over. Can you give me another 45 seconds, and we'll just look at a few quick examples of that formula. So let's look at these problems, and we did all of these problems already today. What do you do with the powers? You divide. So let's just quickly divide x to the 6th, x to the 4th. I think yeah, that's fine. So just go ahead and run down the list and divide all the numbers. It is not at all 6. Right. The thing is, if we're after 210, I'm off the clock and I'm not responsible for saying true things anymore. What's this last one? 18, right? 36 divided by 2. Okay, so then the very last part of this is that some of these need to have absolute value. Some of them are perfect as they are, but some of them we need absolute value. Which ones does the absolute value take revenge on? The even ones. So anything where that number in the front was even requires absolute value from you. So that number in the front is a 12 in this first problem. It's even. The answer is not x cubed. The answer is absolute value of x cubed. The next one. It's a 2. It's even. Any even ones, absolute value gets its revenge. And the one above it is even. And D. Anything where that number in the front is even, absolute value gets its revenge. That's it. The other 3 stay as they are. If you put absolute value, sorry, the other 2. If you put absolute value around those middle 2, it's the wrong answer. The right answer is without. So it's not like you just put absolute value everywhere and it'll be right every time. It's not. You got to put it where it belongs. Okay, so homework is on the next page. I know that was a lot of stuff, but like I said, we're going to practice some more and get better at this. Yeah, I'll take a look at homework that I didn't check during class.